Welcome to Archicraft, a bit of architect, your go-to podcast for modern software and solution architecture, enterprise strategies, and AI-powered engineering. Each episode is AI narrated, based on the original blog content by Dima Golodiuk at demongo.com.
You're listening to the 16th episode of the podcast. This episode is titled, You Probably Do Not Need That Database. In this episode, we explore why a database is a decision rather than a default, and how to choose a store you can defend in a design review. Let's get started.
Picture this. You're sitting in an architecture review. You're maybe 40 minutes in.
Oh, yeah. Everyone's eyes are starting to glaze over by that point.
Exactly. And the team is presenting this brand new service for the enterprise. They're walking you through the API surface, the auth model, the deployment topology.
Right.
And then the architecture diagram goes up on the screen. And right there, sitting dead in the center of it, is a managed PostgreSQL instance.
Naturally. Just taking up half the slide.
Just sitting there like it grew naturally out of the soil. And the crazy thing is, nobody asks a single question about it.
No, of course not.
Nobody asks what data it holds or who writes to it or, how stale that data can actually be. It's just there.
Yeah, it's treated as this inevitable law of physics. Like we see this all the time in enterprise software design. A relational database is just assumed to be as fundamental to the app as the operating system it runs on, or like the load balancer.
Yeah. And that unquestioned assumption is exactly what we are challenging today. So welcome to this deep dive. Today we're unpacking a genuinely provocative article by Dima Golodiuk. He goes by Dima.
Right, and the article is titled, You Probably Do Not Need That Database.
Yes, which is a great title.
Yeah.
So if you're a senior architect, a CIO, a CTO, or really anyone who designs systems for a living, our mission today is to break that automatic reflex of just defaulting to a database.
We want to give you a mental framework so you can make data storage a conscious, defensible decision again. Because right now, the dynamic in those design reviews is heavily skewed.
Oh, completely.
Like if you say, we store in Postgres, that completely ends the conversation. Nobody pushes back. But if a developer stands up and says, we store in 3 JSON files, they're going to face a grueling interrogation from the entire room.
Yeah, the pitchforks come out instantly. And that asymmetry dictates an enormous amount of modern architecture, at least incredibly bloated systems.
It really does.
To kick things off, and just to show how high up this conversation actually goes, there's this fascinating quote from a 2026 interview with Scott Hanselman. He's a VP at Microsoft.
Oh, right, the AI interview.
Yeah, he's being interviewed about AI, and he just randomly pivots and says, people use databases too much. You just don't need a database.
Which is quite a statement coming from a VP at a company that sells massive database solutions.
Exactly. Now, we have to be clear right out of the gate here.
Right.
This is not a war on databases. Databases are incredible feats of engineering.
Right. They're practically magic when used correctly.
Yeah. This is a war on the reflex.
Absolutely. But before we can talk about, removing databases from our diagrams, we really have to understand the psychological and technical gravity that puts them there in the first place.
The forces keeping them locked on the page.
Right. Dima points out a few structural reasons why this reflex is so hard to break. The first one is framework gravity. If you look at modern web development scaffolding, things like Ruby on Rails, Django, Laravel.
Oh, they practically wire in a relational store from day one.
They absolutely do. They ship with object relational mappers, or ORMs. These are translation layers that take your code objects and automatically turn them into database tables. The second you generate a new project, the framework is essentially tapping its foot, waiting for you to define a relational schema.
Yeah, I mean, the default starting point might be a simple local file like SQLite, just to get you coding. But the entire culture of the framework assumes a networked relational database is your ultimate destination.
Right. The moment you move toward a production checklist, you just immediately upgrade to a dedicated database server without even a second thought.
And right alongside that is cloud convenience. I mean, provisioning an Amazon RDS or a Google Cloud SQL instance used to be this massive ordeal. You had hardware procurement, networking.
Now it takes 5 minutes and a couple of clicks.
Exactly.
Yeah.
And the financial cost is entirely deferred. It gets pushed off into this giant aggregate cloud budget that the individual architect simply doesn't have to worry about at the moment of creation.
Which brings us back to that architecture review, right? We have this phenomenon we can call reviewer legibility.
Reviewer legibility, I like that.
Yeah, you put a database on the slide because it's organizationally safe. A clever file-based design invites intense scrutiny because people have to actually understand your specific logic.
Right, they have to think about how you're reading and writing those files.
Exactly. A database is basically an unpriced option for the future. You buy it because of the fear of the unknown future query.
Yes, the fear that your product manager is going to ask for some crazy, complex reporting feature 6 months from now, and you just want the query engine ready and waiting.
We heavily conflate the need for persistence with the need for a database.
We really do. We hear a business requirement that says, this state must survive a server restart, and our brain instantly translates that to spin up MySQL.
Completely ignoring the physical reality that a version-controlled Git repository is durable state.
Yes, an S3 blob bucket is durable state.
A rebuilt artifact sitting on a CDN is durable state.
I always think about this reflex like vehicle ownership. Defaulting to a massive relational database just in case you need it later is kind of like buying an expensive heavy-duty pickup truck for your daily 30-minute highway commute.
Just because you think you might need to haul a refrigerator 5 years from now.
Exactly. You are paying for fuel, maintenance, massive insurance premiums every single day for a capability you aren't actively using. Okay, let's unpack this. If we shouldn't just dump all our cargo into the pickup truck by default, how do we actually categorize the data we're hauling across the enterprise?
Right. So Dima offers a much-needed reframe here. He says we need to stop asking which database should we use and start asking which kind of state are we actually managing.
Okay, so breaking it down.
Yeah, he breaks enterprise state down into 4 distinct categories. The first is reference data. So think about product taxonomies, static country lists, user interface configurations.
Routing tables, things like that.
Exactly. The defining characteristic of this data is that it's read constantly by millions of users, but it's written or updated very rarely, maybe a few times a week or a month.
So its dominant constraint is really just how fast a user can read it.
Precisely. That type of state absolutely doesn't need a query engine. That is usually better served by configuration as code.
Right. You store it in a file, and when a change is made, a deployment pipeline bakes that new file directly into the application.
Yes. Now, the second category is transactional data. This is the state where you have multiple independent actors trying to write to overlapping records at the exact same moment.
Like a bank ledger or an airline ticketing system.
Exactly. You absolutely need mathematically proven oscillation guarantees so 2 users don't book the exact same seat simultaneously. This is the only category that unambiguously justifies a networked client-server database engine.
Got it. Then there's the third category, which is derived data. So this includes your caches, search indexes, aggregated daily reports.
Or read-optimized projections. The defining trait of derived data is that it is never the source of truth. It can always be recomputed from something else.
Right. So the dominant constraint here isn't correctness or safety. It's just the cost of rebuilding it.
Yeah, storing it durably in a secondary system is really just a performance optimization. It saves you the computational time of recalculating it on the fly.
Makes sense. And finally, the fourth category is ephemeral data. User sessions, rate-limiting counters, in-flight coordination between microservices.
Right, the stuff where if a server crashes and you lose this data, nobody is filing a critical support ticket. A user might just have to log in again.
But wait, let me push back here. If I'm a CTO mapping out a new architecture, and I'm looking at these 4 distinct buckets, haven't I just quadrupled my operational headache?
How do you mean?
Well, instead of putting reference, transactional, derived, and ephemeral data into one single convenient Postgres box, I'm now managing 4 different storage architectures. Doesn't that completely contradict the goal of keeping systems simple?
Well, it definitely looks simpler on the architectural diagram to just draw one box, I'll give you that. But the reality is that in almost every enterprise system, the raw volume of reference and derived data vastly outnumbers the transactional data.
Oh, sure. By orders of magnitude, usually.
Right. So when you dump everything into one relational database, you're paying heavy operational rent on transactional isolation guarantees for data that never required them in the first place.
And that single box is incredibly expensive to run. We aren't just talking about the software license fee here.
No, not at all. A database is not just a passive storage locker on a hard drive. It is a massive, complex, standing program that requires constant feeding and watering.
You're buying the operational surface area. When you choose a database, You're committing to designing high availability topologies. You're committing to rehearsed, high-stress backup and restore procedures.
Patch cadences, strict schema governance, and most importantly, you're buying a 3 a.m. pager alarm for an SRE who has to go fix it when it suddenly runs out of memory.
Yeah, the human cost is massive. But beyond that, there's a severe physical performance cost too, right? The network hop.
Oh, absolutely. The article highlights this report from fly.io that compares the latency of in-process databases versus networked databases.
That's squealate numbers.
Yes. If you query an in-process SQL database, which is just a file living on the same physical server as your app code, a query takes about 10 to 20 microseconds. Microseconds. But if you query a vendor-published, highly optimized PostgreSQL instance sitting in the exact same cloud region, that query takes up to 1 full millisecond.
Which, I mean, a millisecond sounds incredibly fast to a human.
Sure, until you map it to a complex application page load. If your performance budget to make an app feel instantaneous is, say, 100 milliseconds, and your code makes a dozen round trips to the database to gather user profile data, settings, content,
you're eating up a massive chunk of your latency budget on network transit before your actual business logic even executes.
Exactly. And you also introduce severe availability coupling.
Right, the database becomes a single point of failure. If your app has a 99.9% uptime guarantee and your database has a 99.9% uptime guarantee, they multiply against each other.
The more network dependencies you have in the critical path, the lower your overall reliability becomes. What's fascinating here is that the massive web-scale traffic we buy all this database machinery for usually never actually arrives.
We build for a tsunami that never comes.
Precisely. There was this landmark paper presented at the HODOS conference in 2015 called the COS paper, which stands for Configuration That Outperforms a Single Thread.
Oh, I remember that one.
Yeah, researchers analyzed these incredibly complex distributed data parallel systems. They found that many of these massive architectures required hundreds of networked processing cores just to match the performance of a competent single-threaded application running on one standard laptop.
Wow. Wait, so hundreds of cores just to break even with a laptop?
Yes, and in some cases, the distributed systems never beat the single laptop at all.
We're constantly over-engineering for big data that just doesn't materialize for 99% of businesses.
Exactly. Jordan Tigani, who is one of the founding engineers on Google BigQuery, recently wrote a piece called Big Data is Dead.
A great title.
Yeah, and after analyzing usage patterns across enormous enterprise customers, he observed that even the biggest organizations rarely queried anything close to the benchmark sizes that database vendors compete on.
Right. Most analytical queries only touch the most recent week or month's worth of data.
And a week's worth of enterprise data usually fits very comfortably in the RAM of one single modern machine.
So if we aren't using a massive, constantly running database to query our data on the fly, how do we actually serve it to users? Because, the stakeholders still need to see their dashboards and their content.
Right.
This brings us back to Scott Hanselman and the mechanics of what he's actually doing when he says you don't need a database.
Yeah, people tend to fixate on the absence of the database in his architecture, but they entirely miss the elegant mechanism that replaced it. So Hanselman runs this site called Tiny Tool Town. Users submit new software tools for the directory via GitHub issues. GitHub acts as the durable source of truth there. When a user visits the website, there is no database query running in the background at all.
It's just flat files.
Exactly. The site is a completely static set of HTML files generated by a framework called Astro. When a new tool is approved on GitHub, a script runs, rebuilds the entire website with the new tool included, and pushes those static files to a server.
So there are no active servers waiting for requests, and no databases computing joins on the fly.
None. He also mentioned his primary technical blog, which he's been running since 2002. The entire content of the blog, about 300 megabytes of XML data, is loaded entirely into the server's memory.
Wow, just sitting in RAM.
Just sitting in RAM. The cache is only invalidated and reloaded when he actively publishes a brand new post.
So the core architectural pattern driving both of those examples is materialization. It's a design where you have a slow, human-paced write path that feeds into a fully pre-computed read path.
Right. It's a very lightweight, file-based implementation of CQRS command query responsibility segregation.
Right, where you explicitly separate the complex logic of writing and validating data from the really simple action of reading it.
Instead of calculating the view every single time a user asks for it, you calculate the view once during the write phase, save the result, and serve that static result to millions of readers.
This pattern completely exposes the corporate myth of real-time data, too. I mean, stakeholders always demand real-time dashboards.
Always.
But in practice, they usually only demand that because no one ever sat down with them and asked, hey, is a 1-hour staleness window acceptable for your business decisions?
And usually it totally is.
Here's where it gets really interesting. Think of this architectural shift like a restaurant. A traditional relational database is like a line cook making every single meal to order entirely from scratch, the exact second a customer asks for it.
Right, that's your live query.
Exactly. It takes time, it takes ingredients, and a sudden rush of customers will completely overwhelm the kitchen. But materialization is a buffet. You cook the food once at a human pace, you set it out on the tables, and then hundreds of people can walk in and serve themselves instantly without ever waiting for the kitchen.
It's a great analogy. For read-heavy reference data or derived dashboards, the buffet model is infinitely more efficient, and it's totally resilient to traffic spikes.
But a buffet doesn't work for every kind of restaurant. And a clever file-based architecture certainly doesn't work for every enterprise.
No, it doesn't.
We have to be brutally honest about where Dima's no database theory hits a wall, because it definitely does.
Oh, for sure. And the article is highly transparent about this limitation.
Yep.
You will not find credible case studies of large enterprises successfully deleting their core transactional databases and replacing them with text files.
Yeah, that would be a disaster.
In fact, the well-documented engineering migrations usually run in the exact opposite direction once a certain scale is reached.
The tail scale migration is the perfect cautionary tale here.
Yes, tail scale.
They're a massive mesh networking company. In their early days, they ran their entire global control plane by serializing their network state dataset into a single 150 megabyte JSON file.
Which is wild to think about. To prevent data corruption from concurrent writers, they protected that JSON file with a mutex lock.
Right.
So a mutex is essentially a software bathroom pass.
Yeah.
Only one process is allowed to hold the pass and edit the file at any given time. Everyone else has to wait in line.
And this architecture was incredibly simple, right? Maybe 20 lines of code.
Yeah.
It allowed them to iterate their product blazingly fast in the beginning.
It did. But they eventually hit a massive operational wall. As their user base exploded, the JSON file grew so large that writing a single commit started taking a full second to complete.
A full second for one commit.
Yeah. And because of the mutex lock, all other network updates were just stuck waiting in a queue. When that latency became unacceptable, they happily migrated their control plane to etc.
Which is a highly distributed key value store, specifically designed for multiple machines to safely agree on state changes over a network.
Right. The critical takeaway isn't that Tailscale regretted starting with the JSON file. It was the absolute right choice for their business, right up until the exact moment it became catastrophically wrong.
Because writing files correctly is mathematically and physically much harder than developers assume. We tend to treat saving a file like it's just magic.
Yeah, and it is notoriously difficult to get right. Dan Liu, a really well-known systems researcher, wrote a brilliant breakdown of a 2014 study by Pillai and other researchers at the OSDI Systems Conference.
Oh, the file system study.
Yeah. The study looked at how complex applications, including Git and Hadoop, write data to file systems. They discovered that developers constantly make incorrect assumptions about how operating systems handle system calls.
Right. We assume that when we tell a computer to save a file, the data is written in order all at once.
But operating systems don't do that. They write data in chunks, often out of order to optimize disk speed. So if an unplanned power event or a hardware crash happens mid-write, those hand-rolled file architectures don't just lose the last update.
They leave behind corrupted, unreadable half files.
Exactly. You think you're saving time by just throwing state into a JSON file, but you are actually building a ticking time bomb for your next server crash.
Which brings us to the true dividing line of this entire debate. The absolute bright line where you unequivocally need a database is concurrent writers to overlapping state.
That's the golden rule. Even the core developers of Starlight explicitly warn against using their engine over a network file system if you have multiple concurrent writers.
The moment many different actors are trying to change the exact same piece of data at the same time, you need a client-server database engine. You need write-ahead logs and complex locking mechanisms to prevent corruption.
You also run straight into legal and compliance walls.
Oh, that's a huge one.
Yeah. If you decide to use immutable files or append-only logs instead of a database, You are going to collide with regulations like GDPR and the right to erasure.
Right, because if an auditor demands that you delete a specific user's data, and that data is permanently baked into a sequence of immutable file histories, you're in trouble.
You are forced to build incredibly complex crypto-shredding architectures.
Where you encrypt the user's data in the file, and when they ask to be deleted, you destroy the encryption key so the data becomes permanently unreadable.
Exactly. This raises an important question regarding organizational maturity. Like, how does a clever file-based design scale beyond the person who built it?
That's a real test.
A hand-rolled JSON storage setup might make perfect sense to the solo developer who wrote the code. It's an elegant solution for an audience of one. But 3 years later, it becomes a nightmare covert contract for a team of 40 engineers spanning 3 different time zones.
Right, whereas a standard database schema acts as executable documentation. It's this universal language that any new engineer can query and instantly understand the constraints of the system.
Exactly.
So if defaulting to Postgres is an expensive reflex, but defaulting to a clever JSON file might corrupt your enterprise data or fail a compliance audit. How does a CTO actually choose a data store they can logically defend?
DEMA provides a brilliant sequence of decision gates for this. Instead of throwing darts at a board of cloud services, you evaluate your specific data against a series of logical tripwires.
Okay, what's the first tripwire?
The first major one is survival. Does the state have to survive or restart at all? If the data is derivable, don't store it permanently, recompute it on the fly, or just hold it in a temporary cache.
Okay, so if it must be stored, the next phase of gates focuses on the writers and the readers. Who is writing it and how often?
Right. If it's just one writer making updates at a human pace, like a content editor publishing an article, a version text file in a Git repository is more than sufficient.
Then you evaluate the reader. How stale can the data be? If the stakeholder can handle data that is minutes or hours old, you pre-materialize it. Build the static file once and distribute it globally via a CDN.
Then you hit the critical boundaries. You ask if the data is entirely local to one process or device, if the data never needs to cross a network. Embedded stores like SQLite or DuckDB are incredibly fast, and they eliminate network latency entirely.
But then we cross the absolute bright line. Are there concurrent writers to overlapping state?
If the answer is yes, the debate ends. You must use a client-server engine.
And finally, you look at future operations. Do you need unpredictable ad hoc reporting? Do you need to prove data lineage and guaranteed erasure to a legal auditor?
Mature database engines have query planners and compliance tooling built right in as first-class features. If you try to achieve that with text files, you're essentially hand-rolling your own compliance framework, which is a massive liability.
It's so interesting to map DEMA's gates against the massive architectural arguments you see online today. On one extreme, you have the just use Postgres for everything movement.
Yeah, that movement optimizes entirely for collapsing the technology stack. Their philosophy is that every new tool requires training, patching, and monitoring. So don't learn 10 different tools. Just use Postgres for your relational data, use it for your caching, use it for your message queues, use it for document storage.
Right. And then on the exact opposite end of the spectrum, you have the just use Squiled or just use files movement. We're seeing incredible tools like LeadStream emerge, which constantly streams local SQLite changes up to cloud object storage.
Making a local file safely durable across server crashes?
Exactly.
That movement optimizes for collapsing network hops and removing fragile moving parts from the critical request path. Both philosophies are totally valid, but they're optimizing for completely different friction points.
It always traces back to Dan McKinley's famous engineering concept of choose boring technology.
Yes. McKinley argues that every company only has a limited handful of innovation tokens to spend on unproven or non-standard technology.
And the trap architects fall into is thinking that a clever, hand-rolled file system is boring just because it's small and doesn't require a server.
It isn't boring. Hand-rolling a custom storage mechanism spends an innovation token just as fast as deploying some exotic, experimental new graph database.
So what does this all mean? The goal of this deep dive isn't to convince you to log into AWS tomorrow morning and delete your core enterprise databases.
No, please don't do that. The evidence for doing that successfully at scale is virtually non-existent.
The goal is to stop you from adding them reflexively, to stop the database from acting as this unpriced option that drags latency and operational overhead into every single new microservice.
Dima leaves us with a highly practical, actionable challenge for your very next design review. Before a managed database instance is allowed to land on the architecture diagram, someone in the room must be able to say this exact sentence out loud.
And the sentence is, "This state is written by these actors at this rate, read at this freshness, and therefore lives here."
If that sentence is easy to say and everyone nods, you have made a rigorous engineering decision.
But if that sentence is hard to say, or if nobody actually knows the answer, you weren't making a decision, you were just drawing a generic slide.
Exactly.
I want to leave you, the listener, with a final thought experiment to mull over. Take a look at your own architecture diagrams right now. Imagine that you had to personally pay a $1,000 fine out of your own pocket every single time a piece of your application's data asked the infrastructure for transactional isolation guarantees it didn't actually need.
That would get expensive fast.
It really would. If that financial penalty were real, how quickly would you redraw your enterprise system? Would that Postgres box still be sitting there, growing unquestioned out of the soil? Or would you finally stop and ask what it's actually holding?
Thanks for tuning in to Archicraft. This episode was generated using AI from Dmitro Golodiuk's blog at demongo.com/news. If you enjoyed this episode, follow the show on your favorite platform and share it with fellow architects and engineers. Until next time, build smart, architect with intent.